This is the 18th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses signed integers. In video 4, we learned how to use binary to represent positive integers in hardware. But what about negative integers? How would you use 4 bits to encode both positive and negative numbers? Pause the video and try to come up with a few possibilities. When asked to devise an encoding for signed integers, most students first suggest adding a sign bit to a binary number. In other words, they're suggesting that we just add one more bit that indicates whether a number is positive or negative. This approach is called sign magnitude. Sign magnitude is appealing because it matches the way we already naturally handle negative numbers. The sign bit is analogous to the plus or minus sign we put in front of integers when writing them out by hand. However, this approach has a couple of disadvantages. The first thing that most people notice is that there are 2 bit patterns that both represent 0. Now, in my opinion, this is more of a quirk than a problem, but it's still worth noting. The bigger issue is that sign magnitude breaks addition. And by breaks, I mean that the traditional longhand algorithm that we base the ripple carry on doesn't work. For example, look what happens when we use the traditional algorithm to add -2 plus 1. The resulting answer is -3, not -1. Now, we can certainly design hardware that will handle this problem, but it's usually better in the long run to avoid problems rather than handling them. So let's see if we can find an encoding that just works with the existing addition algorithm in hardware. Now, because our goal is to use the existing hardware, we'll use binary to encode the positive numbers. Why change something that's already working, right? Now let's pick an encoding for -1 that will work with the existing algorithm. And if it works with the algorithm, it'll also work with the adders we built based on that algorithm. All right, so let's start with -1 plus -1 equals 0. Given that we're using the traditional binary encoding for 0 and 1, what bit pattern do we need to assign to -1 to make the algorithm work? In other words, what sequence of 1s and 0s can we put in place of the x's in order for the addition problem to work out? Pause the video and try to figure it out. All right, let's work right to left. The rightmost sum bit is a 0, and the rightmost input bit is a 1. This will only work out if the other input bit is also a 1. Now let's do the same thing one column to the left. Notice by making the right input bit a 1, there's now a carry in to this column. With that carry in, the x must again be a 1 for the addition to work out. At this point, the next 2 columns are in the same state with an input bit of 0 and a carry in of 1. So after working out the value for each x, we see that the desired encoding for -1 is 1111. In other words, if you encode -1 as 1111, when you use the standard longhand algorithm to add 1, you get 0 as expected. We can apply this same reasoning to see that the encoding for -2 should be 1110. That's the encoding we need so that when we add 1 longhand, we get -1. Notice that if you carry out this process for the remaining steps, you get this. To help you see what's really going on, let me point a few things out. First, remember when encoding unsigned numbers, 4 bits gives you a range of 0 to 15. That is 0 to 2 to the 4 minus 1. When we encode signed numbers, we want about half of the numbers to be positive and half to be negative. So that gives us a range of -8 to 7. 8 is half of 16, so we get about half of the numbers below 0 and half at or above 0. This half and half split also has a convenient side effect of letting the most significant bit act as a sign bit. As I mentioned earlier, the positive numbers are encoded the same way they would be encoded in binary. But when the leading bit flips from 0 to 1, when in binary we'd go from 7 to 8, 0111 to 1000, we let that be the transition from positive to negative numbers. And it's at this point we do something a little bit different and clever. We take the first bit string that begins with a 1, which is 1000, and assign it to the lowest value we can represent with 4 bits, which is -8. By doing this, as the values increase, like from -8 to -7 to -6 and so on, then the bit patterns also increase from 1000 to 1001 to 1010 and so on. As a result, our existing adders just work. These adders always make the bit patterns progress or increase, so we want to make sure that when the bit pattern progresses, then the corresponding number increases. Contrast this with the sign magnitude approach, where it's the absolute value of the number that increases, not the actual value. Of course, the transition from -1 to 0 is noteworthy. It relies on the fact that bit sequences act a little bit like odometers. When you get to the all 9s on the odometer, it rolls back around to 0. Well, when you add 1 to the last bit pattern of 1111, it rolls back around to all 0s. But notice this isn't as much a special case as it is just a convenience of how the math works out. So if you see a number in 2's complement form, how do you interpret it? How do you convert it to decimal? Well, first, remember how binary works. Each column is a power of 2. So when you have 1101 in binary, you have 1 times 2 to the 0 plus 0 times 2 to the 1 plus 1 times 2 squared plus 1 times 2 cubed, which is 13. 2's complement is similar. It just makes one change. The leftmost column has a negative value. So in this case, the place value of the leftmost column is -8 instead of +8. So what we're doing when we look at a 2's complement number, if it begins with a 1, we start with a negative value and count up. So in this case, we begin with -8 and move up 5 to get -3. Now what we're looking at here is the formal definition of 2's complement, the formal specification of what each place value is. However, in practice, when working with negative numbers, we use one of 2 shortcuts. The first technique is to flip all the bits and add 1. So for example, to write -3 using 2's complement, first we would write 3 out in binary, 0011, and then we would flip all the bits to get 1100, and then add 1 to give 1101. And if we place this back into the formal formula, we see that that works out to -3. Okay, now you try it. Pause the video and write -22 in 2's complement. Okay, so we write 22 in binary, 010110, flip all the bits, 101001, and then add 1, which gives 101010. We place this into the formal formula and we see that it does in fact encode -22. Notice that in the first step, when you write the number in binary, you need to include an extra leading 0. So there's room for the sign bit. +22 only technically needs 5 bits because the range of a 5-bit number is 0 to 31. But the range of a 5-bit 2's complement number is only -16 to +15. 22 is outside of this range, so we need a 6th bit. Now this technique of flipping the bits and adding 1 works in both directions. So try it out. What is 1001 in decimal? Well, flip the bits, 0110, add 1, that's 0111. So 0111 is 7, which means the 2's complement value is -7. Now try 101101. Well, flip all the bits, 010010, add 1, 010011. Well, in binary that's 19, so that means our answer is -19. A second shortcut is to flip the bits to the left of the last 1. Let's see what that means when encoding -3. So we write 3 in binary, 0011. The last 1 in this case is the rightmost bit, so we flip all of the other bits, giving us 1101 like we saw before. All right, now try it using -22. Okay, 22 in binary is 010110. This time, the last 1 is the second digit from the right, so we flip everything before that and get 101010. And like the first shortcut, this one also works in both directions. So use it to find the decimal value for 1100. This time only the leftmost bit gets flipped, which gives us 0100, telling us that this is the 2's complement for -4. All right, last one. What is 101100 in decimal? Well, flip the 3 leftmost bits. That gives us 010100. That's 20 in binary, which means we've encoded -20. All right, one last thought before we wrap up. Given a bit string, how can you tell if it's 2's complement or binary? Trick question, you can't. Remember, a bit string is just a pile of ones and zeros. There's nothing inherent in the string that makes it binary or 2's complement. Whether a string is binary or 2's complement is entirely a matter of how you choose to interpret it. That's why when you look at wires and pins in JLS, you see both the binary and the 2's complement value. There's nothing about a circuit that determines what the wires mean. Their only meaning is the meaning that you give them when you look at the wires. That may be a confusing idea for the moment. I remember it took me a little bit to get my head around it. We'll be sure to revisit it a few times throughout the semester. All right, let's wrap up. The main thing you should be able to do based on this video is, of course, convert between decimal and 2's complement, both directions. You should also be able to determine the range of values that can be represented using 2's complement with n bits. So for example, if I ask you what signed numbers can you represent with 6 bits, you should be able to tell me that you get a range of -32 to +31. And finally, you should also be able to explain the reasoning and the advantages and disadvantages of the different encodings we talked about, signed magnitude and 2's complement. In the next video, we'll see how to use these signed integers for addition and subtraction.